Hey guys, today I wanted to go over with you curve sketching with transcendental functions. So figuring out, for example, the critical values of a natural log or an exponential function, or determining where the absolute mins and maxes are, where are the points of inflection, where does the concavity, so different things like that. We've done this all before, just now we're looking at it with natural log with e to the x. So the first question we're going to look at says find the extreme values of f of x and give intervals of increasing, decreasing. So we didn't actually call these extreme values, we called these critical values when we were looking at them. But just know they may use that language too. So our function is f of x equals the natural log of x. So critical values occur at a few different places. So remember that critical values happen when the derivative of f of x is 0. They also occur when the derivative of f of x is undefined or does not exist. Okay, so in order to find the critical values, I've got to find the derivative. So if we're finding the derivative of f of x here, this is a chain rule problem. We can see that the outer function is u squared. The inner function is u. Okay, if you want to use u substitution here, you can. If you just want to rely on chain rule, that's fine too. So with chain rule, you bring the 2 to the front because it's a power rule problem. Inside stays the same. And you drop the exponent by 1. So now there's an exponent of 1 on the outside. And then you multiply by the derivative of the inside. The derivative of natural log is 1 over x. If you wanted to clean this up just a little bit, you could, but it doesn't really change much. You can kind of change it to 2 over x times the natural log of x. Okay, so now we need to figure out where is this 0 or where does it not exist. So to do that, you can kind of look at each piece. So first of all, I can look at this portion and say, where would that equal 0 or where would that be undefined? It's never going to equal 0. There's never a value of x I can plug in that would cause that to equal 0 because there's not a 0 in the numerator. The only way to make it undefined is if I make x 0. So I'm going to put x equals 0 as a possible critical value. Because again, 0 would 2 over 0, or any number over 0 is undefined value. The next part I have to look at is, what about ln of x? When is that 0? So there's a few important points that you need to know on the natural log function. Okay? And these are the 3. So these 3 you would be expected to know without a calculator. So for example, the natural log of x is never going to reach 0. The domain of x is greater than 0, or natural log x is x greater than 0. So that's important for you always to know unless it's shifted to the left or right. This one is not. Another important point to know on the natural log function is the natural log of 1 is 0. So the natural log of 1 has an x value of 0, and then the natural log of e is 1. They are inverses, they undo each other. So I know that the natural log of x would be 0 whenever x equals 1. So those are possible critical values. And the reason that I say that is because this is actually not a critical value. And I want you to think about it. And we talked about this just a second ago. The natural log of 0 is undefined. It doesn't exist. It's not even in the domain. If you look at this natural log graph that I posted, it gets close to 0, but it never hits it. 0 is a vertical asymptote. So because of that, because it's not in the domain, it can't be a possible critical value at all. So that means the only critical value I have here is x equals 1. Okay? And then the next portion of this question says, give intervals of increasing, decreasing on f of x. So to do that, I can make a sign chart. And I know this ends at 0, so I'm not even really I'm going to do an open dot here because we don't want to include 0. The critical value I found was 1. So I need to know what's happening on this graph on both sides of 1. Okay, so I'm going to pick a number, so say 0.5 and a 2. All right. Now, we can use our calculator to this. We can use our knowledge of natural log for this. Okay. So, for example, if I do 2 over 0.5, I know that that is a positive number. The natural log of 0.5 is a negative number. I can do that by plugging that into my calculator or having the knowledge that the natural log of 1 is 0. So if it's less than 1, it's going to be negative. So I can see here that my graph, or that my derivative is negative on the left side of 1. And then if I plug in a 2, I get 2 over 2, which is positive. The natural log of 2, since 2 is greater than 1, that's also positive. So I can see that my graph is going to be, or my derivative is going to be positive on the right side of 1. So I know that f of x would be decreasing from 0 to 1 and be increasing from 1 to infinity. Okay, so I've got my critical value. I'm going to erase all this over here now that I've kind of talked about it already. But I've got my critical value. Hey guys, my recording paused on me, so if I'm repeating any of this or if it skipped around a little, give me some grace. I apologize for that. But we are going to continue on. So this problem, I wanted to review with you extreme value theorem. And just to refresh your memories, remember that extreme value theorem just guarantees an absolute min or an absolute max on an interval, as long as it's continuous and differentiable. So I gave you the graph of g of x here just because I wanted you to see that it is continuous and differentiable from -1 to 1. But if we think about this, the graph of just y equals x is continuous and differentiable. The graph of e to the x is also. So if we put them together, they're still going to be continuous and differentiable. This would be a calculator active problem because it can be difficult to find the values you need. Although I would say we could probably do it without the calculator too. So it would be possible for us to still solve this. Okay. So since I want to show you how to do this one in the calculator, in order to find an absolute min or max, there are, remember, 2 places where those can occur. So an absolute min and max can occur at endpoints. So it could occur at -1 or 1. And then it can also occur at critical values. So where the derivative is 0. All right. So if I were doing this in my calculator, what I would start with first is by looking at the endpoints. Okay, so we want to evaluate g of 1. We also want to evaluate g of -1 and see what those y values are so we can figure out which one's the highest, which one's the lowest. To do this in your calculator, you would put your original function in y1. So in y1, I'm going to put x times e to the x squared. And then I would hit second calc and number 1, which is value. And then I plug in the x value that I want to find. So if I do that with positive 1, I get 2.718. If I do that with, repeat that same process with -1, I get -2.718. Okay, so we can clearly see which one's the highest and lowest out of those two. So the only other thing we have to consider is critical values. So remember, critical values occur when the derivative is 0. So in y2, I'm going to put the derivative. I don't actually have to find that mathematically. I can remember do second calc and 6, or it's not second calc 6, I'm sorry. Yes, second calc 6 to do that. So if I do this, I'm going to put in y2 d dx, y1, I don't have to type in the function again, and we want the entire derivative, so we put x equals x. Okay. Once I do this, I'm looking for where does this cross the x-axis? Where does it cross the x-axis? Okay. And then if I actually look at this graph on the interval from -1 to 1, it doesn't cross the x-axis at all. So there are no critical values. Okay, if you find the derivative, e to the x can never equal 0. It just doesn't. Okay, it never crosses the x-axis on its own. The other part of the derivative, you end up getting 2x squared plus 1. If you set that equal to the 0, you get that x would be plus or minus the square root of -1/2, so you get a non-real solution. So there are no critical values on that interval at all. Okay? And so since there are no critical values on that interval, my absolute min and max must be the two endpoints. So I could say regarding g of x that the absolute max is 2.718, and that occurs at x equals 1. Remember, it is the y value, it occurs at the x value. My absolute min is -2.718, and it occurs at x equals -1. So that's an example of extreme value theorem for you. All right, next example we're going to look at is just some quick particle motion. So just to refresh your memory on particle motion, remember S of t often stands for the position of the particle. V of t stands for the velocity of the particle, and then A of t is the acceleration. Okay? If you're finding the derivative, you go this way. And remember, when we start integrating, we go that way. So if we integrate acceleration, we get velocity. If we integrate velocity, we get position. Okay? And then there's other things we can tell about the function by looking at its velocity. So for example, say that we want to figure out when the particle is moving to the left or right. We can use the velocity to figure that out. When the velocity is greater than 0, it's moving to the right, not equal. When the velocity is less than 0, it's moving to the left. We aren't going into this, but remember, when velocity and acceleration have the same sign, the particle would be speeding up. When the velocity and acceleration have different signs, it would be slowing down. Okay, so those are just a few things about particle motion that we kind of looked into. All right, so since we want to find in this problem the velocity and use a sign chart to describe the motion, okay, we need the derivative, because remember, velocity is the derivative of position. So if I wanted to find the derivative of S of t, okay, I should put dt here. So remember, it's e to the x again, whatever your x is, and then times the derivative of the exponent. The derivative of the exponent here is the cosine of t, positive cosine t. So we need to figure out, where is this derivative going to be 0? Okay, so when does v of t equal 0? Because if I can figure out when it's 0, then I can use that information to figure out when it's moving to the left, when it's moving to the right. Okay, so we can use our calculators to do this for us. And just like in the last problem, so we would plug in the derivative, and you can plug it straight into y1 if you want, or you can put the original in y1 and then put the derivative in y2. So just put your derivative somewhere, wherever it makes sense to you. And then we can do second calc, and 2 would find our zeros for us. Okay, so if you calculate that out, you should get 2 zeros. One when t is 1.571, and one when t is 4.712. From there, I can make a sign chart to try to help me figure out, when is that going to be positive, when is that going to be negative. Okay, And then if I look at values, or if I look at the graph of the derivative even, I can see that on the left side of 1.571, my velocity is positive. In between those two critical values, it's negative. On the right side of 4.712, it's positive. So I can see that my function goes from increasing to decreasing to increasing. So it's moving right, then switches and starts moving left, and then starts moving right again. And hopefully you've seen that in your calculator. I didn't want to go through the details just because you just looked at a problem like this. This just uses the word velocity in motion. So I wanted just to make sure that you could translate that vocabulary. Okay? Last problem we're going to look at today is using the second derivative to find points of inflection and concavity. So remember, points of inflection happen when the second derivative, why am I spelling occur the way I am? When the second derivative is equal to 0 or does not exist, and changes sign. So it's got to go from negative to positive or positive to negative around it. Okay? When the second derivative is less than 0, we can say that the original function is concave down. And then when the second derivative is greater than 0, we can say that f of x, the original function, is concave up. Okay, so we're actually going to try to see if we can do this one without a graphing calculator, okay? So by hand. So first thing I need to do is actually find the second derivative. Okay, so this might be a little bit of a process, but we can do it. So let's start with the first derivative. Okay, so first derivative, remember when you're taking the derivative of an exponential function, okay, that it's the same function repeated times the derivative of the exponent. So I'm just going to repeat the same function, e to the negative x squared, then I'm going to multiply by the derivative of that exponent, which is negative 2x. So that would be my derivative. If you wanted to rearrange that, you could. We don't have to because we're going to be finding the second derivative anyway. So now let's talk about the second derivative. Well, we can see that there are two pieces to the first derivative. They both have x values. So when we find the second derivative, we have to use product rule. So product rule says, first off, do 1. Just repeat the first part. Then times d2, which is negative 2, plus 2 d1. And the derivative of e to the negative x squared we already found. That's negative 2x times e to the negative x squared. I just moved the negative 2x to the front. And so let's clean this up and try to make it look a little better. So negative 2 times e to the negative x squared plus his negative 2 times negative 2, 4x squared times e to the negative x squared. Okay, so if I just have this written down, I can't tell a lot about g of x, or the second derivative. So let's see if we can factor something out to make it look a little better. So I could factor out an e to the negative x squared. When you do that, I'm also going to go ahead and pull out a 2, because why not? So I'm left with negative 1 in that first position, plus 2x in the second position. Now this is something I can deal with a little bit better. So the first thing we have to look at is this 0 or undefined ever? So we can look at the first piece of the function. That isn't 0 or undefined ever. Okay, that actually never occurs. And that should be, I'm sorry here guys, that should be x squared. So that never gets to a 0. So now we're really just focusing on when is this 0. So if I set that piece equal to 0, okay, and solve that, I can trust that you do that algebra and pause for a second and actually do it if you need to. But you get x equals plus or minus square root of 1/2. Okay, and luckily it was positive square root 1/2. okay? If you wanted to simplify that, you could, like, rationalize the denominator and everything. That would be 1 over root 2. If you rationalize that, that's plus or minus root 2 over 2, but you don't have to do that. Okay, so now what we can do is make a sign chart. I'm going to delete this graph. I just kind of wanted you to see it. But we're going to make a sign chart with our critical values. And remember, this is using the second derivative. So we're talking about concavity and POIs. So I'm going to put my lower one here, my upper one here, and we need to figure out what's going on in between. So I can find some test points. So maybe 0, -1, and 1 to kind of look at. And remember, you don't have to find the exact values. You just have to think about them, okay? So if I think about putting -1 into this derivative, okay, so here that would be e to the -1, okay, or 2 over e, if you want to think about it that way. Well, that's going to be a positive value, okay? Now, if I put -1 in the next piece, I get -1 squared, which is +1. So I get -1 plus 2. That is also a positive number. So I can see here I'm multiplying a positive by a positive, so the second derivative would be positive, meaning the function would be concave up, okay? Now I need to figure out what's going on at 0. I'm going to use a different color to do this. So we'll use orange. So if I'm writing in orange, I'm talking about x equals 0. So if I plug in 0 here, I get e to the 0. Well, that's just 1 times 2. That's a positive. If I plug in 0 here, I get 2 times 0. That's 0. Plus -1 is a negative. So I have a positive times a negative, which means that the second derivative is negative from in between our two critical values, so f of x is concave down. Last number I have to plug in is +1, so I'm going to do this in purple. If I plug in +1, I get e to the -1 again, so that just becomes 2 over e. That's a positive number. And then if I plug in a +1, I get 2 plus -1, which is a positive number. So positive times a positive is a positive, so f of x is concave up in that interval. And so now I know my intervals of concavity. I also know that I have 2 points of inflection, one at negative square root 1/2, one at positive square root 1/2. So then I could write out my intervals of concavity from there. All right, guys, hopefully this wasn't too bad for you guys. It's just, again, reviewing material that we've already been over just now with some transcendental functions to make you think a little bit more about it. But hopefully it'll be a good review session for you to get ready for the exam. Bye, guys.